Okay, thank you. Hello, everyone. Good afternoon, guten Tag. Uh, I'm Youssef. I'm from Evidence, especially on the R&D team on Spain, based on Spain. And regarding my presentation, I advise you, I barely talk about CFDs, a bit of CICDs, and the presentation is basically based on programming GPUs, okay? So CFDs we all use them, and they are really good tools to simulate real world behaviors. But probably you try to paralyze them, and you also suffer paralyzing them. And the classic idea to paralyze them is having let's say, CPU code, which we can split on different batches and throw it through different nodes on a cluster, right? But why not going a bit farther? We can try to go with GPUs, which is a good idea, trying to saying that GPUs are really good architectures for massive parallel algorithms. And talking about GPUs, you probably heard about NVIDIA GPUs, which are the most famous. But in the case we would like to go with GPUs, you must know that there's an issue. We have more than one vendor. There are different vendors. The most known is NVIDIA, but we also have AMD, or recently Intel has joined to the group of GPU vendors. And the main issue we have here is that programming GPUs does not have just one only language. We have different languages. In the case of NVIDIA, we have CUDA, right? In the case of AMD, we have the toolkit ROCm and the programming language of the vendor, which is HIP. And in the case of Intel, we have one API or its own language maintained by Intel, which is level 0. Okay. So then the main issue is, okay, we would like to go with a GPU, but which language we should use? Probably you might say, let's go with NVIDIA. But in that case, I would say, imagine in 1 year, 2 years, the next most powerful GPUs would be AMD, which is now probably the most powerful GPU. And what in the case of another vendor joining to the team? We should move all of our code already ported to GPUs to another vendor language. So in a traditional pipeline, CI/CD pipeline, probably you have this kind of structure, right? Let's say in our case, we are programming with GPUs. We are going with NVIDIA, which is the first step in our pipeline, the code. And this is probably the typical CI/CD code. What in the case we would like to maintain different codes from different vendors? So then we probably should include code from different vendors and complexizing our CI/CD structure, because we are using different compilers and we are maintaining the code from different languages. So is there any alternatives? Yes, they are. And I would like from now on talk about portable languages and native languages. Let's say that native languages are those maintained by the developers, by the vendors, and we could say that they are CUDA, HIP, or level 0. The points of these kind of languages are that they are dependent on each platform, as we said, and they have a compiler for each architecture. However, they offer us the best performance we can achieve on that architecture. We can go then with OpenMP, which you probably use for parallelizing CPU code. It has a version which is called OpenMP offloading, which we can use to parallelize code on the GPU. But And the idea of OpenMP offloading is we have the same code and we can run it on different architectures, right? However, the OpenMP code has been still compiled with different compilers from the different vendors, at least if we would like to tie it with the best performance. And what about the performance between moving to the native language to OpenMP? That's what we are going to talk in a few next slides. Another alternative is cycle. In this case, we are saying that as well as an OpenMP, we have the same code. And in the case of cycle, we can tie it on just one compiler. So in this case, we have just one compiler and we can write the same code and run in different architectures. And you also may know that there are all alternative, OpenCL, Raja, Cocos, but we are going just to stick with Cycle, OpenMP, CUDA, and HIP in this presentation. Regarding the experimentation, this is the setup. We employed an NVIDIA V100. We use, in the case of AMD, a 6700, and in the case of Intel, a Intel Max 1100. And the performance is not really important because we are going to compare the performance of different languages in the same GPU. So we are not going to compare different GPUs from different vendors between them. And regarding the code, the next part of the experimentation is the toolkits we are using. In the case on the V100, we are using CUDA 12.4 to run the CUDA code and the OpenMP code. In the case of AMD, we are going to use ROCm 5.4 to use the HIP and the OpenMP code. And lately, in the case of Intel, we are going to use its compiler to run the cycle code in all the GPUs, because it supports all the other vendor GPUs. And also, in this case, the compiler also supports OpenMP, but just for the Intel GPU. Regarding the benchmark configuration we use, this is all the benchmarks we use. There are most of them CFD benchmarks and also other known applications used in the area. There is the reference if you want to see the parameters and the configuration for each benchmark. So let's go with the results. First thing is we have 3 different bars in this plot. The green one is CUDA, Cycle on orange, and OpenMP on blue. Okay, in this case, the code was failed on the case of OpenMP in that benchmark, the D3Q19, mostly because in the original benchmark it wasn't implemented. We also failed on the mini-weather application because the interaction between Cycle and OpenMP in just this case had been failed and we couldn't fix that case. And regarding the performance, which is I'm trying to show you in this architecture, in the V100, by moving from CUDA to Cycle, we are just losing in average 9% of performance, of the native performance. The case of OpenMP, we are losing about 20% of the native performance. Now moving to the AMD GPU. In this case, we don't have the green bar, we have the red one, which is the HIP one. Again, the first benchmark it wasn't implemented. And in this case, the lead-driven KVT benchmarks fails because some memory allocations, because OpenMP tries to allocate more memory than the driver led the backend. And regarding the performance, in this case, the performance was very poor. In the case of Cycle, is like 66% of the heap time. However, we noticed that there were 2 cases in the ADV, in the advection, and in the mini-weather benchmarks, where probably the code was not the most efficient. And trying to avoid this standard deviation, removing them and recalculating the average, we can say that mostly is 81% of the heap performance. In the case of OpenMP, it was like 51% of the performance. We are halving the performance by moving from the native language, which is heap, to OpenMP. And we didn't see any specific cases which the performance were specifically poor. So in the case of OpenMP, we saw that the performance is really poor in this platform. Lastly, on the Intel GPU, in this case, we have the main issue with the main mini-weather benchmark because it uses MPI, and this GPU were used on the Intel cloud, and we didn't have the root access to install MPI. So basically, that's why it failed in this platform. And regarding the performance and the Intel GPU, we saw that in this case, level 0 and cycle over, there's one thing I didn't say, which is in the case of Intel GPUs, the main language we use is level 0, but most of the code is programmed on cycle and uses level 0 as backend. And we also have the opportunity to use OpenCL as backend in the Intel GPU. And both backends in this case are pretty similar in performance. In the case of moving to OpenMP, this is the only case we found that moving to OpenMP was a bit faster, in this case, 5%. So one last remark before going to the conclusions is that notice that we are talking about, let's say, high-level languages, and at the end, the code we are running on the architecture is assembly, right? And well, lately is 1 and 0s, but before going to 1 and 0s, we are running assembly. And the assembly code in these platforms, in the case of NVIDIA, is called CUDA-PTX, and in the case of AMD's AMD GCN. And I would like to mention that in the case of running the CUDA code, transforming from CUDA to CUDA-PTX, the number of lines which are translated to the NVIDIA assembly is 33,000 against 46,000 in the case of using SQL and transforming it to the assembly. And in the case of OpenMP was mostly like 144,000. Okay? In the case of AMD, it was even worse. Notice that on heap, transforming to heap to AMD GCN was like 23,000 against 43,000 against 132,000. So regarding the conclusions, I think that this kind of languages, the native languages we talk about, have some lock-ins, and they are probably not the most beneficial for CI/CD pipelines because we have to move to more complex pipelines. And this kind of portable languages, we talk about Cycle, OpenMP, but there are all the others, such as OpenCL or Cocos, would benefit in this kind of processes. However, in the case you would like to have the most efficient performance, you still have to stick with the native languages tied to each vendor. And however, we saw that SQL has some promises. It depends on the platform, but we are on the Intel GPUs with the most efficient language. In the case of AMD, it was a bit poor, and in the case of AMD, was like losing 9% of performance. In the case of OpenMP, we saw that we have mixed results, especially really bad on AMD GPUs. And that's all. Thank you.